Limiting reactant. At least I believe that people who don't know anything about chemistry are missing an important source of happiness, just being able to understand things. But clearly I'm biased. We talked about reaction stoichiometry, and a lot of you guys will have had some practice with this yesterday, so a lot of this should just be reviews, reinforcing stuff that you had to teach yourself. So this is a chemical reaction. Gasoline is a lot more than just octane, but we're going to simplify things, we're going to talk about it as if it's octane, and this would be the balanced chemical equation that would explain or would represent that process. Burning gasoline, producing carbon dioxide, and water. I will say, different than Alex, I try to break things up more. So there will be questions about, can you balance a chemical equation? And then here's a balanced chemical equation for this one. Now do the stoichiometry. That makes it a lot easier for me to grade for one, because it breaks apart those two things. Because if you do the balancing wrong, then you're going to get stuff wrong in the equation, and that makes it harder to grade. I'll give you things more piecemeal, but you did get a lot of good balancing practice. Most of the time when we're burning octane, what's the limiting reactant? When we're burning gasoline. Okay, you're not wrong. Oxygen is. But what makes your car stop? Yeah, we can always pull in more oxygen, and you could run your engine so that it burns way more efficiently. Yes, there is a perpetual issue. I think the best efficiency anybody's ever gotten is like 50%. And it was Mercedes and a Formula One engine. So, yes, assuming everything's perfect, though, the thing that you're going to run out of first is the gasoline, right? Because we can just keep pulling in oxygen from outside. And that's the idea that follows with limiting reactant reactions, right? Something's going to run out first, and then there's going to be leftover oxygen. Now, in the case of a gasoline engine that's pulling in oxygen from outside, we're not going to calculate how much oxygen there is in the atmosphere on Earth, right? Our pool there is unlimited. In the context that we'll be talking about, there will be limited amounts of both of the reactants, and you have to calculate which one runs out first. So in our reaction stoichiometry, we're always going to be following the law of conservation of mass. So like up here, we have the coefficients that tell us how many of each molecule that we need to do this reaction. I need 2 octane molecules, 25 oxygen molecules, then I'll get out 16 CO2 molecules and 18 water molecules. The key thing that I want you to understand is that I said molecules on purpose, or atoms, because the reaction stoichiometry is for the individual atom or individual molecule scale. But we scale that up. So it'd be the same thing if I say moles, it's just like saying a dozen, right? I need 2 dozen octanes to react with 25 dozen oxygens. I'm just scaling everything up. So when we talk about this, we'll talk about a mole ratio, because we could talk about these numbers in terms of the atoms and molecules, which is what they actually represent, and in terms of moles, which is what we're actually going to use on sort of a real world scale. And that's why we get fractions and stuff in the number of moles used or the number of moles produced. But it is happening on a one-to-one. If you could measure precisely enough, you would see that. So yeah, stoichiometry is this study of the numerical relationship between quantities in a chemical reaction, and then using those quantities to make predictions about a reaction. So food recipes are a great example, or a great analogy for this, because it's often very similar, especially when you consider something like pizza, where you're gonna have one crust. Of course, you can make smaller or larger crusts. So super simple cheese pizza recipe, 1 crust, 5 ounces of tomato sauce, and 2 cups of cheese gives you 1 pizza. And we can express the relationships between things with the ratios, these coefficients. So you can say, if I have 1 crust, then I'm going to need 5 ounces of tomato sauce, or 2 cups of cheese, or 1 pizza. And those are all interchangeable, and we can use any set of 2 that we need for whatever we're trying to calculate. So if I had 3 crusts and I wanted to know how many, actually here, if I have 10 cups of cheese, so if I have 10 cups of cheese and I want to figure out how many pizzas I can make, then I would use the ratio of cups of cheese to pizzas. So 2 cups of cheese would give me 1 pizza. So 10 divided by 2 equals 5 pizzas. But we could say from that 10 cups of cheese, we could also calculate how many ounces of tomato sauce we need and how many crusts we need. So from that one thing, saying, if I have a limited amount of this, how much of everything else do I need? And in my mind, they all work like gears, right? If I turn the cups of cheese gear 10 times, it's locked in with all of these other things that also have to move at set ratios. So we do the exact same thing with chemical reactions. So we've got all these coefficients. So this could be 2 octane to 25 oxygen, or it could be 2 octane to 16 CO2, or it could be 2 octane to 18 H2O, or any of the other possible iterations. And I always refer to this as a, oh, I guess I was supposed to do this. Did I leave myself in a room? I refer to these as mole ratios. It's the ratio of moles needed in the chemical reaction. So if we burn 22 moles of C8H18, and you could do railroad tracks, or you could just do right amount as fractions. Then I need 2 moles of C8H18 to produce 16 moles of CO2. That's math that I can't do in my head. And I don't have a calculator. 22 times 16 divided by 2. So that's 176 moles CO2. All right, everybody good on those parts so far? Yeah.
What it's not specifically noted, what being asked about reactants?
Just said reactants instead of CO2?
We want to know.
Oh, how much of the other thing would be used?
Yeah,
or left over?
We have the whole thing backwards. Like we have values for CO2 reactants. I got the reactants.
Yeah, if you have one of the products, the thing that's weird about the way that you've set that up is that if we have, like, the reactants are made in a fixed ratio to each other. So if I produce 16 CO2s, I get 18 H2Os. So from either of those, I could go back and calculate how much octane burned and how much oxygen was used from either of them. And they should both give the same number.
So it's the same thing. It's just your stoichiometry reverse.
Yeah.
Through the equation, just the same.
Yeah. So nothing changes mathematically. Yeah, these mole ratios are the key to solving any problem with this reaction. Yeah, so if it said I produce 36 moles of H2O, how much octane burned? I say 36, and this is 18 to 2. So divide by 18, multiply by 2, and you would get however much octane that is. 4, B4. Yeah, so we can pick any combination and calculate in any direction. And the way that I'm going to show you how to do limiting reactant stuff is going to be a little different than from what Alex does. I think it's easier, but that's the way my brain works. Huh?
So say you're not given an exact, like us giving you a decimal, so you would have to use that mole ratio to figure out how, like,
The mole ratios were always exact.
like you could in the equation, like there was 8 was one of the ratios, and then they give you like 9, you still have to figure out that one by using the ratio.
Yeah, so like here, if I did, even if it was like 1.5 moles of octane burns, how much CO2 would be produced? That kind of thing. So if it was, let's do it, 1.5 moles of C8H18. So again, and this is what I was saying, the actual chemical reaction, chemical equation, these are per molecule, but we scale it up to 1.5 moles because that's 1.5 times 6.022 times 10 to the 23 molecules of octane. It's a whole bunch of molecules. So I can have 1.5 because basically we can't even really figure out if we're calculating if we have down to the single atom or molecule, because the level of precision that we need would be insane. I'm sure there's a way to do it, but anyways, so here we would just use the same ratio. So 2 moles of C8H18. You want CO2 or water? Water. So it'd be 18 moles of H2O. Oh, forgot my calculator. So 1.5 times 18 divided by 2. So you'd get 13.5 moles of H2O. Does that kind of answer what you're thinking? Okay. So in some ways, when we switch from doing moles to moles and we do mass to mass, we're just adding a translation layer on the outsides of the same conversion. So we're getting our numbers now, instead of in moles, we're getting a mass of A. But in the chemical equation, those ratios are in moles or molecules. So I have to convert it from mass into moles, and then I can use a mole ratio to get the amount of any other thing in the chemical reaction. And then finally, if it asks for you to convert it to grams, then you do that conversion at the end. So stoichiometry at its core is this middle part. And we're just translating numbers from a mass into moles, or later we'll do solution concentrations and volumes into moles, or we'll do gases, because the way we describe an amount of gas is different. We need pressure, temperature, and volume. But ultimately, it's always to get back to moles before we do a conversion, and then go back out to whatever the requested units are. And so to get from mass to moles, that'll always be molar mass. And we'll use a molar mass over here. And then in the middle is the mole ratio. Okay, great example of a word problem that includes useless information. Flavor text, if you will. All right, according to the US Department of Energy, the world burned 33 times 10 to the 10 barrels of petroleum in 2013. The equivalent of approximately 3.7 times 10 to the 15 gallons of, or grams of gasoline, not gallons. Calculate the mass of CO2 emitted. So what's the useless information here? Yeah, we don't need barrels for this, so we just ignore that part. All we need is grams of gasoline. 3.7 times 10 to the 15 grams. And then we're going to assume that the gasoline is all octane. That's just an approximation to make our lives easier. Yeah, you'd have to figure out a way to either separate, well, both separate and then analyze what those things are. In what? There would be different equations, yeah. Octane that's burning, it's going to be this. If it's heptane, that's 7 carbons, it's going to be slightly different. And so you'd have to have an equation for each one and then the amount of each component. Yeah. So it says calculate the mass of CO2. So we'd go back to grams. Yeah. So yeah, we need the molar mass of octane. Nope, not mode. So that's 114.26 every 1 mole octane. Okay, and then what's the mole ratio from octane to CO2? To 16. So if you don't have a balanced chemical equation, then you need to get one or figure one out before you can do this. And then we got to go to CO2. I'm only writing the CO2 and the octane on one side of it, but it applies to both. So 3.7 times 10 to the 15 times 16 times 44.01 divided by 114.26 divided by 2. So this is going to be 1.1 times 10 to the 16 grams of CO2. And yes, you can simplify the mole ratio if you want to, right? The math comes out the same. Whether or not you do 16 and then you divide everything also by 2, or if you do 8 and 1, it's the same thing. So the thing to remember for stoichiometry is not to memorize any specific steps, like dividing by molar mass or multiplying by molar mass, but it's to remember, if I have a mass, I need to get to moles, because we did, I guess I'll say, mass. So we went from the mass of A to the moles of A, then to the moles of B, then to the mass of B. And there's no conversion factors here to memorize either. Right? This is fundamentally a unit conversion problem, unit analysis. We just look at the fact that we started with grams. If I need to go from a mass to moles, then I need the molar mass. Look it up on the periodic table, do a little bit of calculating, and then you plug it in so that the grams cancels out. And then that will leave you with moles. So now that I have moles, how do I convert from moles of one thing to moles of another? It's going to be a mole ratio. So that's what we do there. Now I want to go back to a mass. Mass to moles is just molar mass again. And you don't even need to remember multiply or divide. Just write it out as grams per mole and then cancel out the units. Okay. Do you want to get to limiting reactants? Okay. Let's do these again real quick. I'll go through them fast, but I'll post this video on YouTube so you can come back to it. Okay, so what mass of HCl in grams is neutralized by a dose of milk of magnesia containing 3.26 grams of magnesium hydroxide? So what's the only number we were given to start with? 3.26 grams. And it's also in the chemical equation, so we need a molar mass for that. Magnesium's like 24 or something. Thank you. 24.305. So plus 16 times 2 plus 1.01 times 2, 58. So 58.325 grams, 1 mole. Okay, what are we trying to calculate? Mass of HCl, right? And now we got moles of magnesium hydroxide. And what's the mole ratio? Yep. So there's a 1 there. We don't write the 1 in, but it's there. So 1 mole of magnesium hydroxide, 2 moles of HCl. And so if we wanted to put into English what we're doing with these, I want to put into English, what does it mean to use this mole ratio? If I start with a mass of magnesium, what is the question that what am I saying when I calculate a mass of HCl? If I go from one reactant to another, I'm saying if I start with this much of one of my reactants, what I'm calculating is how much of the other reactant gets used. I should practice going the other way because that's the way you guys see it. So I calculate it with one reactant, the magnesium hydroxide. So starting with this, when I calculate from magnesium hydroxide to HCl, that tells me how much of the HCl that I need or how much will be used up when this reaction happens. 3.26 times 2 times 36.46 divided by 58.325. 4.08 grams of HCl used or neutralized or reacted with. So if I told you there was 10 grams of HCl present at the beginning, how much HCl is left over? That would do how much I started with minus 4.08 grams, should give you like 5.92. haven't quite gotten to it yet, but that's the idea with a limiting reactant, and then the leftover reactant really is you start out, usually you don't know which one's going to be your limiting. So you do some calculations, you figure out the limiting, but then when you take the limiting reactant and you calculate the amount of the other reactant used, then you can calculate how much was left. Subtract it out of that starting amount. All right. So again, flavor text up top, one component of acid rain. All right, the generation of electricity used by a medium-sized home produces about 16 kilograms of nitrogen dioxide per year, assuming that there is adequate oxygen, water. What mass of nitric acid in kilograms can form from this amount of nitrogen dioxide pollutant? So why is this adequate oxygen and water thing important? Yeah, it's something we've ignored from the other questions and it's something that I think is easy to forget about when you just see stoichiometry as the math, because you forget that when I do a calculation like this last one, I start out with this magnesium hydroxide, I crunch a whole bunch of numbers, then I come out to this 4.08. I'm like, great, that's how much got used. But for that to happen, there has to be this much HCl in the first place. This has to be present. So like there I said if there was 10 grams, but if there was less than 10 grams, or if there's less than 4 grams of HCl to start with, then we wouldn't have enough to do that reaction. And in something like this, it's asking about this product, but it only gives us the 16 grams of nitrogen dioxide. So we don't know how much oxygen, we don't know how much water. So that's why they throw in here, well, assume that there's enough of those. And really, when you're doing any of these calculations, you're assuming enough of everything else. Yes. Yeah. And actually, the way that Alex words these questions also, how do they word it? They say calculate the maximum possible amount. And what they're doing there is they're putting in that aside, which maybe can be confusing. You probably learn to just ignore it. What that really means is most of our chemical reactions don't actually go 100%. It's like we were talking about with even burning gasoline. Gasoline does not burn 100%. Diesel, especially when people roll coal, that rolling coal, that's unburned diesel that's coming out the back, unburned products. So if the reaction doesn't go 100%, we'll talk about this more in Chem 2, then you won't make even the maximum amount. You'll get something less than that. But we're assuming almost all the time that we do make the maximum amount, just like we assume a lot of the time that there is adequate amounts of other things in the reaction. Okay, so 16 kilograms of NO2. What's the first thing that we have to do on this one? Yeah, we gotta get to grams. That'll be 1 kilogram. It's 1,000 grams or 10 to the 3 grams. And then this will be 14.01 plus 16 times 2. And I know we're going through these real fast, but I want you to see this pattern, right? Every single time it's get into moles, convert moles, go back to grams. And later we'll do other things. So then my mole ratio from nitrogen dioxide to what? Sorry, yeah, I changed it up on you. HNO3, but it is 4 to 4. So 4 NO2 to 4 HNO3. And again, even though that would just simplify to 1, I encourage you just put it in there as 4 to 4, do the multiply by 4, do the divide by 4, because if you come back to your notes, it'll be easier to understand where those numbers came from. Okay, and then nitric acid is going to be 63. So that's 63, and then, oh, this is the part that's easiest to forget or easiest to overlook, is it wants our final answer in kilograms. So 1,000 grams, 1 kilogram. So let's tell us how many kilograms of nitric acid get produced. So 16 and 21.9. Oh, I guess it is 2 sig figs. Hello? No, it doesn't want it. Okay. There it goes. 22. So there's another conversion here that I could have left off. And still gotten numerically the same number. Kind of like multiplying by 4 and then dividing by 4. We divided by, or we multiply by 1,000 and then divide by 1,000. So end up undoing that conversion. Okay. Yeah.
So you don't have to do like a conversion, because you said it right. Or
Yeah, so I won't mark you, I won't mark it wrong if you do everything correctly and get the correct answer. But it's something you do have to look out for, because if this had asked for the answer in grams, then it'd be different. So you need to change that. But if we're going from kilograms to kilograms, then you can leave those off, because you end up doing it and then undoing it. Yeah. All right, limiting reactant theoretical yield. So our reaction here, oh yeah. Again, coming back to the fact that this reaction equation is written with the individual molecules or atoms in mind. So it's 1 magnesium hydroxide is all that I need, but then I would need 2 molecules of hydrochloric acid to produce 2 molecules of water, 1 molecule of magnesium chloride. And most of the time, we don't have the same amount of reactant or product, or I guess of either reactant is what I meant to say. So we have some amount of magnesium hydroxide, we got a slightly imperfect amount of hydrochloric acid for that reaction to happen, right? Because again, we're doing things at a scale of moles. So being off by even a 10,000th of a milligram could be billions and billions more HCl molecules in total. So what we want to know is what happens when we do run out of one, and how do we figure out which one we run out of first? So go back to our pizza analogy. If we have 4 crusts, 10 cups of cheese, and 15 ounces of tomato sauce, then how many pizzas can we make? So you could say from the 4 crusts, if it's 1 crust to 1 pizza, we'd say that's 4 pizzas. So can I make 4 pizzas? Maybe, I don't know yet. I don't know, we have to calculate the other ones, right? So that's one of those assumptions. Oh, I got 4 crusts. This is if you went into, your pantry or your refrigerator or whatever, and you're like, oh, there's 4 pizza crusts. I can make 4 pizzas before you check to see if you even have the tomato sauce or cheese. You're making an assumption that those things do exist in quantities, in high enough quantities. So if we've got 10, I'm just going to write cheese. So we need 2 cups of cheese. Will give me 1 pizza. So that means with that, I can make 5 pizzas. Looking good so far. But that 5 pizzas calculation assumes enough crusts and enough tomato sauce, right? So it doesn't looked at, because they're not part of the calculation, it hasn't looked at those other things yet. So now we know we can't make 5 pizzas, but we're still okay for 4 pizzas. And then with 15 ounces of tomato sauce, that though needs 5 ounces for 1 pizza. So that's only 3 pizzas. How many complete pizzas can we make? 3. Now, the thing that's different between things like making pizzas is we could make one sad pizza that had lots of cheese but no sauce. We can't do that with molecules, right? I can't use less than 1 molecule in a reaction. And this is the way that I go through calculating out these amounts, because it's what makes sense to me. It's the least complicated in my mind. So basically, we start with each reactant, and we'll calculate how much of a product can I make. So if there's 2 different products, pick one. Ideally, if there's another question about like what's the maximum amount of this thing that can be made, pick that one, right? Because then you'll figure it out in the process. And then whatever makes the least amount is the limiting reactant. So in this one, our tomato sauce was the maximum number of pizzas that we can make. Whoops. Would be our theoretical yield. And remember this maximum number, theoretical yield, and limiting reactant, those things are all tied together. Whatever the limiting reactant makes is the maximum yield, even though it's the smaller number. And it's the theoretical yield because, in theory, that's all we can make.
Theoretical yield can only be established if we have a plan of what the reactants gram measure.
If you have, you could do for moles too.
Something I have to have some measurement on the
Reactants.
reactant.
Yeah.
Otherwise,
Kind of.
the equation itself.
Yeah. It'd be weird to, yeah, I can't envision a way at least a question would be asked that way. So you could say, in theory, I want to make this amount of a product. How much do I need to start with to get that theoretical amount? Because there is an amount that would lead to your product in some amount, right? So you can't kind of, yeah.
To do that, you just calculate the grams off of the moles from the equation.
You're never going to start with the moles from a chemical equation, because they are just telling you about this in general. Like our pizza recipe tells me that if I had one crust, then I could make one pizza.
Right. So then I could say if I wanted to make X amount of pizzas, I just need to have that much of crust.
Yes. Yeah. Okay. I see what you mean. Yeah. The reactant that limits the amount of product. So the one that puts a limit on things is the limiting reactant. And then the other reactant, that should be green. Reactants not completely consumed are said to be in excess. So we have to calculate how much gets used before we can figure out how much is left over or how much is in excess. Oh, I don't think there were questions on this on Alex, but just like most things, I didn't have it up here, right? If I burned some pizzas, or if I don't have a dog, but if my dog ate them, or if my cat ate a pizza for some reason, or walked over it with cat litter on its paws, then I would throw that pizza away, and my theoretical or my actual yield would be lower than my theoretical. Right? Everything going right, I could get 3 pizzas, but now Mochi has rolled on one because he's a fluffy little terrorist. I don't think he would ever, but then that ruins one of the pizzas and that reduces my actual yield. Now, actual yields have to be determined by doing the experiment. It takes a lot of other things into account. To calculate an actual yield, it's just what percentage of the theoretical yield could I make? So it'll always be smaller, and there's no subtraction here. It's just actual yield divided by the theoretical times 100. Really wanted to get to one question. Wow, okay, we got a ways to go before doing one. All right, so I'm going to do this again super fast. So we've got 2 different reactants here. They're both making, right, react together, they produce magnesium oxide. It's 42.5 grams of magnesium. And then our other equation that we're going to do is 33.8 grams of oxygen. Now, this is where my method differs from Alex's. Alex at this point would say, start with magnesium and calculate how much oxygen is going to be used. Then from oxygen, calculate how much magnesium is used. And for my brain, that is very confusing because you're crossing these things, and now you started with numbers of magnesium and oxygen, and you ended with numbers of magnesium and oxygen just flipped. So it'd be really easy to mix those up. So instead, we're going to use, just like the pizza thing, we're going to say, how many magnesium oxides can I make? Starting with this much magnesium and then this much oxygen. Whichever one makes the smaller amount is the one that runs out first. And it gives us the added benefit of having then the theoretical yield of magnesium oxide even after this first part. So this was 24.305 as 1 mole. And then that's 2 magnesium to 2 magnesium oxide. And then this would be 30.305 1 mole. This is 32. And 1 mole. And 2 moles. Also, when you do it this way, if you go all the way to grams, then you just get to reuse the same molar mass. I guess the other way you get to reuse molar masses too, but okay, so 42.5 times 30.305 divided by 24.305. So that is 52.9916. No, I did something wrong. This is 40. Did not math that correctly. The dangers of mental math. Gosh. So it's actually 70.5. 33.8 times 2 times 40.305 divided by 32. There you go. It's 85.14. So 85.1 grams. Now these are both magnesium oxide. Which one's my limiting reactant? Magnesium. So it's limiting reactant. And then my theoretical yield. Yeah, so the theoretical yield is what the limiting reactant makes. Now, if I wanted to find the leftover of the oxygen, right, because I ran out of the magnesium first, that means that there's going to be some oxygen left over. I would just do another stoichiometry problem, go from magnesium to oxygen, and then whatever amount of oxygen that calculates, remember from one reactant to another reactant says how much of this other reactant gets used. Subtract that from the starting amount, and that tells you what your leftover is. Yeah, I think that's an easier way. Unless if Alex's way made sense to you, by all means use that. Makes no difference to me. There's two ways of doing the same thing. So